Well, this article is about those paradigms that use some scores and then use CKY algorithm to create the graph. So I'm explaining this article, span-based hierarchical semantic parsing for task-oriented dialogue. And so it is inspired by some articles like a minimal spanning-based constituency parsing in 2018 with a self-attentive encoder, and also 2018 semantic parsing for task-oriented dialogue. So let's see how we can resolve this problem. So the task-oriented parse, so TOP stands for task-oriented parse. And it's a very restricted task. When we say task-oriented, so even the categories that we choose are very restricted to a kind of dialogue that can be set. So first, as I said, top is a tree representation. So it has intents and slots. What is your intention? For example, getting direction. What is your slots? For example, slot destination is just a slot for the intention, get direction, and so on. So our parser is span-based. It scores labels of the tree nodes covering each token span independently. This is independently. But then decodes a valid tree globally, like the CKY algorithm. So you see that it introduces edge scores. So it's not just node scores, but we also have edge scores, which model relations between parent and child labels to mitigate the independence assumption between node labels. Because this is another source of expression for these models, because the more you add these information, the more accurate it becomes. So we propose a span-based semantic parser for parsing utterances into top representation. For example, when we say span from 2 to 5, it means John's party. For example, in this figure, John's party is here from 2 to 5, span from 2 to 5. And so there are two contributions. The first contribution is that the training method is faster than using margin loss, because we are using, as I will explain, we are using kind of cross entropy. So it's like multi-class classification, and there is nothing to worry about CKY at the training. But still, we need CKY at inference, of course. But at training time, we don't need, because we are just doing a simple multi-class classification problem. And we are not worried about. We are just comparing the predicted label for each node to the gold label for each node. So it's just cross entropy classification. We just use the cross entropy loss. And this is a unary chain, for example, destination to find event and so on. So for our span base, it is helpful to view the tree as a mapping. For example, when we say span 2 to 5, it means SL organization in field and find event and destination. So if there is, and we have a rule, simple rule. If we have no terminal covering the span, we said this is null, like this. These, they're nothing. But we need at least 2 to 5 in order to make it, for example, say it is a destination and find event. So our model is like this. So our parser is based on a joint distribution over the chain at the span. So the probability, this is the probability of span I and J having chain C. Be a softmax, so it's a probability, as I said. and we normalize, so it's normalized, so it's probability, and this is the probability that span I and j have chain, it has chain C. So it's a node score. So n here spans for node. Later, I will show you that we also have a score for edges. So to compute the scores, we embed the span using our technique, which is LSTM-based span from 2017. But even before that, we knew that if you have an LSTM, here we have an encoder, then these are good representations. For example, if it is 2 and 3 and 4, when we say what is the span 2, 4, we just say, okay, this is Hij. I give it to a forward neural networks, and it becomes a scalar. A scalar is a good score, so we can use it later. And after we have finished training, because now that we have this log, this sum of log, what is sum of log? Sum of log of probability of t. We know that probability of t equal to c is equal to that. So log of exponential fn, so this cancels, so it becomes fn remains. And then after that, but here we cannot omit that because it's a summation. We cannot say that log of summation of exponential, we can cancel that. So here we can cancel log with x. It goes 1, it becomes 1. So what it remains is fn here. But the rest of that, we should keep it. But because it does not depend on t, so ignore it. You just need to learn this. So it becomes as simple as this, the summation over all node scores. And then at the test time, we can use CKY chart parsing to decode a valid tree. And so there is no need for CKY training time, of course, because traditionally we used to say that we have max margin loss and those, but for each step you need to evaluate your CKY algorithm. So it becomes very slow. And suddenly the authors of this article, they're very smart. They noticed that we can think about it as a multi-class classification. There is no need to get involved with the CKY algorithm at the training time. Still, we have to use it for inference, but at the training time, we don't need that. So that was the story. And so later we will see that how we can think about it. So it becomes this. And so the class weights for empty chains, so in practice, the number of spans with gold chains equal to none is large compared to the total number of spans. To avoid this, we scale it. Because you're using cross-entropy laws, we can just use a hyperparameter to tune which kind of labels we have it is dense or it is sparse. If it is sparse, we can tune it. If it is dense, it's okay. But if it is sparse, we can tune it. We can reduce the amount of that and penalize it. So motivation for edge scores is that the model so far scores each span independently. So it becomes suboptimal. So if we can have more information, for example, edges, then we can have better accuracy. The prediction of top intent only depends on the embedding of X, which is equivalent to standard intent classification. Similarly, ontology constraints are also not captured by the model. So this is the edge scores. But here we have for the parents as well. So if the parents of I and J has label L, For example, the parents is like L1, L2. This is, for example, L1. This is L2. So if we keep L1, so the probability that the parents is L, given that the spans for the labels are C for category C for span IJ, then we say that it's now we are using edges. This is edge. Remember, it was for nodes. Now we have for edges. So it's just a softmax of. So this is equal to softmax of f of edge of this span. So everything is a standard, and later, so now we have, as I said, I've explained this part before. The same thing happens for edges. So these are the same thing for edges. Nothing strange. Everything is crystal clear. And then we talk about tree score because now we have nodes and also we have these parents. Because for the same analogy, we can say that the second part doesn't contribute. It's not dependent on T, and therefore we can just reduce the tree score to this beautiful formula. And P is the softmax over edge scores. And then the training loss is sum over cross entropy for span and cross entropy for each edge. So if you sum, then you get what you want. And for a data set, if you click on this, a file will be downloaded, which looks like this. For example, lots of rows. For example, one row is that, will I make it to the beach by noon if I leave now? And in the second column, it is this program, let's say. So get estimated arrival, and then we can say it's destination. This is a slot, but a slot could be an intent for a higher level. So it's hierarchical. That's why the name of this article suggests. So this is the location, and this is the date time arrival. And look, it doesn't work like Chomsky that every parent has only 2 child. But here you see that sometimes you have 3 child. No problem, we can still use it. And the accuracy. It's really interesting. This article, with no edges, with no edges, they have an accuracy of 80%. If they add edges, just 1% improvement, and the time is almost the same. But what is important, the F1 score is almost the same. The error types. Sometimes you have wrong top intent. Sometimes you are missing non-terminal. Sometimes you're joining 2 gold non-terminals. So the error type is like that. So for this, it becomes 20, it becomes 26, and that's it.